Okay, with this video, we're going to start talking about our graphs of sine and cosine and the alterations we can do with them uh, by adjusting their period, amplitude, phase shifts, and vertical translations. Of course, we have to define what all these things are, but let's start by looking at the graph of the sine graph, which we should all be well familiar with. You should have seen the previous videos as to how the sine graph um, was drawn based on the unit circle, following the y coordinate as you move around counterclockwise around the unit circle. So we refresh you. As you can see now, the x-axes are marked off in whole number units, but you've got to imagine that these are actually values of pi. So we know that the sine is equal to 0 at pi over pi. So here's our value of pi, right to the right of 3.14. Here's our 6.28 value. The pi over 2 value here is 1.57. So just so that you are exposed to some graphs will depict it in numerical values, as you see here. Others, more often than not, will depict it in fractional values of pi. Okay, so we know that the sine is a periodic function, that it repeats itself again and again and again. Every revolution around repeats the other wave. That's the nature of trigonometric functions, and that certainly is the nature of the sine graph. Okay, every revolution around the unit circle depicts a wave. Okay, so the function repeats itself every 2 pi radians, which is every revolution. So we call the period, that is the shortest interval that defines the entire graph. The period is 2 pi. Okay, we should agree that the domain is all reals, because the graph goes on repetitively again and again and again, although the range is here limited to between -1 and +1 inclusive. Okay, that is our range. Okay, we have something that's called the amplitude, which commonly people think of as the height of the function, but I'm going to caution you against that. I'm going to give you this definition. Amplitude is the highest value minus the lowest value. So the highest value here is 1, the lowest value is -1. That's the highest value minus the lowest value divided by 2. So it's 1 minus a -1, which is 2, over 2, which is 1. And I give that definition because in time we're going to shift this function up or down, or stretch this. So we want something a definition that's going to be consistent with all the future changes that are going to come via the via the adjustments to the function. So the revolutions, the 2 pi period is a cycle, a revolution, a wavelength, all one and the same. Okay, because of the periodic nature, because of the repeated pattern with the function, because it repeats itself every 2 pi radian. If we shift the function by 2 pi left or right, we essentially shift the function onto itself. If I were to take and say, okay, let me impose a horizontal shift of 2 pi, well, okay, this whole portion graph negative would just graph into this positive portion. Likewise, if I shift it in the other direction, it would fall right back onto itself. But remember, the graph just keeps on going and going and going. So chances are you wouldn't even see any change. So we end up with a very well-known identity, okay, which is very indicative of all periodic functions, that if you shift, okay, a horizontal shift of the function by its wavelength, or any multiple of its wavelength, it shifts right back on itself. So this becomes a what we call an identity, a trigonometric identity. It's defined here as a translation, horizontal translation, based on the periodic nature of the function. You can pull this up on your calculator, and if you said, okay, let me in y1 graph the sine of the function, y2 let me graph the sine of x plus 2 pi or minus 4 pi or plus or minus any multiple of 2 pi. You won't see any difference in the graph because it just shifts it onto itself. So that becomes known as an identity. Okay. A item that I always like to stress, okay, is that the sine function is going to cross the axes at the beginning, middle, and end of its cycle. The beginning, the middle, and the end of the cycle. The cycle being 2 pi, it crosses right there at the beginning at 0, then halfway through, and then when it's finished or when it starts again. Okay, beginning, middle, and end. And again, that's a consistent statement because what we got to remember is there's going to be alterations to this. This graph is going to be stretched and compressed horizontally, but this item here that the graph will always cross the beginning, middle, and end is going to be a consistency. Okay. You can also see that the sine function is symmetric with respect to the origin. Okay. In other words, okay, if we pivot the right half of the sine graph around the origin, it would, by 180 degrees, it would fall right onto itself. We knew that when we talked about functions in general, that if you reflect a function across x and it ends up giving you the same thing as if it were reflected across y, which is noted here, reflected across x is the same difference as if reflected across y, okay, then that is a function, that is a quality that's indicative of function symmetric about the origin. And since the sine is indeed a function symmetric about the origin, it gives rise to this identity. The sine of a negative angle is the negative sine of the angle. The sine of the negative angle is the negative sine of the angle. And we're going to start building our repertoire of all these identities, which are going to largely come to us via the graphs. Okay, so let's now talk about our good friend, the cosine function. Okay. Again, the cosine function, just like the sine function, is periodic in nature. Okay, it repeats itself. It repeats itself every pi radian. Again, here I've reiterate that we're marked off in whole number units, but it's the same. Okay, here is pi over 2, 1.57. Here is pi at 3.14. Here's pi 6.28. So those are in fact those are in fact our values of pi. Okay. The one thing that differs from the cosine from the sine is the fact that it crosses over the x-axis at a quarter way at the quarter and 3/4 marks of its period. Okay. In other words, at its 3/4 and quarter mark, or a quarter way of the way in from either end, the beginning or the middle, okay, will mark where it crosses the axis at a quarter and 3/4 of the way through its interval. Okay. Again, like we said, the function repeats itself every 2 pi. The period is every 2 pi. Okay. The function is ongoing. Therefore, its domain is infinite in nature. All right, taking on every value of x, but limiting itself in y to being between -1 and 1. The amplitude, same as the amplitude for the sine function, the highest value minus the lowest value over 2, which gives us an amplitude of 1. And again, this formulation is good to keep in mind, anticipating vertical shifts down with future graphs that we'll look at. Okay. Again, same thing as we said, period, amplitude, a period, revolution, wavelength, all imply the same thing. We find that periodic nature in the cosine graph as we have with the sine graph, giving rise to this identity here, that you shift the cosine graph by any multiple of its wavelength, it will simply shift right back onto itself and gives rise to this identity. Okay. You can see here that the cosine function is in fact symmetric about the y-axis. The cosine function is symmetric about the y-axis. Okay, it is a mirror image of itself across the y-axis. Okay, when we had functions that were symmetric about the y-axis, we once referred to them as stupid function, not knowing the difference between a positive and negative x. Therefore, the function evaluated at at the opposite of x gave the same thing as the function evaluated at the positive value of x, and therefore, since the cosine has that quality, it gives rise to this property that the cosine of a negative angle or the cosine of an opposite angle is the same as the cosine of the positive angle. That's why cosine is both positive in the first and fourth quadrant. Okay, cosine of 30 is the same as the cosine of negative 30, either of which is root 3 over 2. Cosine is also, as you know, we take a look at reflected across the x-axis. It's the same in the second quadrant as it is in the third quadrant, both being negative. Okay, so we're going to kind of put a hold on the show here for now and come back and resume after this slide with another video. But there you have some properties about cosine and sine that that you want to remember. Okay.